Welcome to this video on continuous casting, where we explore the engineering behind integrated production, process control, and how it drives manufacturing efficiency.
Continuous casting represents a major shift from traditional batch-style ingot casting. Instead of creating individual ingots that require cooling and reheating, this process casts molten metal directly into continuous slabs, bars, or sections, forming the heart of modern steel production.
The batch route is inherently inefficient. It relies on stop-start operations, requires heavy logistics to handle solid ingots, and wastes massive amounts of energy by cooling metal completely, only to reheat it later for rolling. Continuous casting removes these unnecessary steps.
Anatomy of a continuous casting machine includes 4 main stages: a molten pool for a steady supply, a water-cooled mold to initiate the solid shell, a roller path to guide the material, and finally, the output of solid bars or slabs ready for processing.
The water-cooled mold is the heart of the process. It is open at both ends. Water cooling forms a solid shell on the exterior, while the core remains molten. This incomplete solidification is exactly what allows the casting process to continue without interruption.
Continuous casting relies on a moving boundary between the molten interior and the solid exterior. The position of this solidification front depends on 2 key variables: the cooling rate and the speed at which the casting is withdrawn.
The mold is an active system. To facilitate movement and prevent sticking, it is constantly vibrated and lubricated with a graphite-type material. These mechanisms are essential for maintaining smooth, continuous production.
The withdrawal mechanism pulls the casting out of the mold. Rollers play a dual role here. They transport the heavy material along its path while providing the necessary mechanical support to prevent deformation of the weak, partially solid shell.
Safe operation requires a critical balance between cooling and withdrawal speed. If the metal is withdrawn too quickly, the shell will be too thin, leading to a liquid breakout. Precise control ensures the shell is thick enough to hold the molten core.
Continuous supply is the core constraint of the process. Because the metal must remain physically connected to the molten pool at all times, any interruption to the supply will cause the entire casting process to stop immediately. Continuous casting also eliminates common defects. In batch casting, shrinkage creates a pipe or cavity at the top of an ingot, which must be cropped and discarded. Since the continuous process fills the mold steadily, this defect is effectively removed, improving yield. Beyond material yield, this method removes the need to maintain thousands of individual ingot molds and significantly reduces the splashing and spatter defects often associated with pouring discrete, individual batches. Comparing the 2 methods highlights the clear advantages of continuous casting: continuous operation, reduced energy intensity, elimination of piping problems, and a more streamlined, integrated flow towards further processing. Continuous casting illustrates a foundational manufacturing principle, combining sequential operations into a continuous, integrated process whenever physics allow, which enhances energy efficiency, material flow, and overall manufacturing economics. To summarize, the 3 pillars of continuous casting are the core mechanism of continuous flow, precise process control, and improved manufacturing economics. Next, we will look at sand casting and how it differs from this approach.